Hello students, welcome to this module on basics of hydrodynamic stability, which is part 4 in this series of modules on this topic. This is part of the course CHE 614 at IIT Kanpur. What we were trying to do in the last couple of modules is to introduce you to the so-called method of normal modes. Okay, so the idea here is that when we linearize the NavierStokes equation, okay, why are we linearizing it? We are linearizing the Navier-Stokes equations because the perturbations are considered to be very small. Perturbations are considered to be infinitesimal. Therefore, we can linearize the Navier-Stokes equation. The meaning of linearization is, of course, that neglect terms that are non-linear, in the sense that if you have a product of Vx prime times partial Vx prime by partial Vy or something like that, right? These are products of two fluctuating quantities. So these are non-linear quantities, and these quantities are neglected. The reason is that if you have a small number, let's say 0.01, if this is the amplitude of the disturbance, if you multiply 0.01 by 0.01, you will get 10 to the minus 4, which is much small compared to 0.01, which is 10 to the minus 2. Okay, so this is the rationale behind neglecting nonlinear terms. Therefore, the moment you neglect the nonlinear terms after substituting that the velocity is given by the velocity vector is given by the base state velocity vector plus fluctuations, and neglect nonlinear terms, what you will end up is a set of linear coupled time dependent partial differential equations. Now, the most important thing to solve a set of differential equations is to prescribe the boundary conditions and initial conditions. For example, if I were to ask you to solve the unsteady heat equation, which is partial temperature by partial time is equal to thermal diffusivity times partial squared the Laplacian of temperature in 3 dimensions. Okay, now in order to solve this, you have to specify, okay, let's even simplify it to 1D. We'll just keep partial squared t by partial x squared to simplify our discussion. In order to solve this, you have to specify boundary conditions, namely at x is equal to a and x is equal to b, what happens to the temperature, what at this temperature or the derivative of temperature. Some boundary conditions have to be specified at 2 locations. Why 2? Because you are solving a second order differential equation in space. You need 2 boundary conditions in space. Now, in addition, you also need initial conditions, right? So the initial condition arises because you have a time derivative, first order time derivative. You need one initial condition. Usually you will say that at time t equal to 0, the temperature in the domain at t equal to 0 is some known value or known function or whatever it is. So this has to be prescribed or known in order for you to solve this unsteady heat equation. So initial condition and knowledge of initial condition is a must. Initial condition is necessary to solve a linear PD or even a nonlinear PD. Now, if you look at the linearized Navier-Stokes equations, let's go back to hydrodynamic stability. If you look at the linearized Navier-Stokes equations, what what you will find is that you have a set of linear PDEs. Okay, and you will definitely have boundary conditions. Typically you have no slip conditions or any appropriate conditions for the domain, but we have no idea about initial condition. No idea. That's because in any given experiment, laboratory experiment, the initial condition is a completely random quantity, completely random. So in most laboratory experiments, so you have no idea about initial condition. Then how are you going to solve the PD? Here is where the method of normal modes comes. Okay, here what we are saying is that because we don't have a knowledge of the initial condition, we will abandon or we will completely get away from the hope of solving the problem with a specific initial condition. Instead, we will try to see whether we can comment on the stability of any arbitrary initial condition using the method of Eigen Function expansions. Okay, so here what we said in the last lecture was that suppose I have any quantity f of x, y, z, t. This is some disturbance. Okay, some disturbance. Let's say it can be the x component of the velocity or pressure or whatever. Now we took a specific example. Now the specific form of this Eigen Function expansion will of course depend on the geometry and configuration. Here I took a case where, for example, this is the x direction, into the screen is the y direction, perpendicular to the wall is the z direction. Let's say there is some flow in the x direction, alright, and there are some no slip boundary conditions. Okay, at the two boundaries, and the x and y directions are infinite in extent. Okay, now the z direction is bounded and there are boundary conditions. Let's say no slip. Now if I were to express an arbitrary function of velocity, let's say, in an Eigen Function expansion, okay, now along the x and y direction I will use continuous Fourier transforms, okay, because they are infinite in extent. I'll use Fourier transform, and along the z direction I will have to use some kind of finite Eigen Function expansion. Okay, now let's try to write this. So we'll write this as summation, okay, n is equal to 1 to infinity. This is summation over this Eigen Functions in the z direction times minus infinity to infinity dkx. Kx is the wave number along the x direction, minus infinity to infinity dky. Okay, now you will have a function of a subscript n, because along the z direction it is n. So these constants will be functions of kx, ky time, and you will have Eigen Functions Vn of kx, ky, z times e to the I kx x, e to the I ky y. Okay, this is the most general form of the expansion of the any arbitrary disturbance for this domain, wherein you have two infinite directions and one finite or bounded domain, which is the z direction. Now because You can now imagine arguing that, well, you have a if you substitute this all in the partial differential equations, you will get a set of ODEs for an, and those themselves can be thought to be solved by Laplace transforms if you wish, or you can say that because these are all linear PDEs which are first order in time, the time difference has to be exponential. So we can write this as some an cap times e to the st, and this s itself is a function of n kx ky. Okay, this s is called the growth rate of perturbations. Now this is the most general type of expansion. Okay, now we cannot, of course, if you were to solve this, then you will have to specify initial conditions, and we don't want to specify initial conditions. In that context, I told you, in a finite dimensional space, suppose you have some linear problem like this, either you solve this as an initial value problem and write x of t in terms of some Eigen function expansion, some c1 e to the lambda 1t v1 plus c2 e to the lambda 2t e2 v1. The eigenvectors are v1 v2 and corresponding eigenvalues are lambda 1 lambda 2. So this is the Eigen function expansion. I is equal to 1 to n ci e to the lambda I t vi. Now these two expansions are analogous. The only complication here is that you have a higher dimensional function, and therefore things get a little more complicated. But ideally speaking, this ci's are these ans, e to the lambda I t is e to the st, and the eigen vectors become these combination of eigen functions because of the higher dimensions involved, and being a continuous variable, x, y, z being continuous variables. Now you can either fix these constants using initial conditions, that at time t equal to 0 if you know what is x naught. If you don't know initial condition, suppose initial condition is not known, we can comment on whether things are going to decay in time or grow in time by looking at just the eigenvalues. So in the method of normal modes, we don't use the superposition of eigenfunctions. We merely try to find out a representative term in the eigenfunction expansion. You substitute this back and solve only the eigenvalue problem. So the method of normal modes is equivalent to solving the eigenvalue problem by abandoning the initial value problem. The reason why we abandon the initial value problem approach is because we do not have a precise knowledge of the initial condition. Okay, so the method of normal modes can also be thought of as the eigenvalue based approach. Okay, now the thing that I told you about the method of normal modes is that if even one of the lambda i's is positive, that is, if its real part is positive, then perturbations will exponentially grow in time. Okay, so the system is considered unstable. Okay, now you may ask the question, what if my initial condition does not have that particular eigenvector? Okay, let's say you have lambda 1, lambda 2, lambda n. Let's say lambda 1 is greater than 0 and all the other eigenvalues are less than 0. Let's assume them to be real for the moment. Otherwise you can think of them as real part of the complex number lambda. Right? Now if you say that my eigenfunction expansion of the initial condition does not have this eigenvector corresponding to lambda 1, then of course that special initial condition will decay. But we are not interested in a very specific or special initial condition. We are interested in arbitrary random initial conditions wherein if you expand this, you will have in the eigenfunction expansion all the lambdas, all the eigenvectors, lambda i's and vi's, corresponding eigenvectors. This means that even if one of them, then the sum will blow up. So in the method of eigenvalues, you don't try to satisfy initial condition. In the method of normal modes, you merely calculate the eigenvalues and then see what happens. So this approach will give what is called asymptotic stability or instability. The reason is that you can comment on what will happen as t goes to infinity. If all the eigenvalues are less than 0, then as t goes to infinity, definitely you can conclude that the sum will decay to 0. And similarly, if all the eigenvalues, this is stable, even if one of the lambda i's is greater than 0, you know that the sum is eventually going to blow up in time. The system is unstable. So this part is very clear. Even if one of the eigenvalues is positive, real part is positive, then the system is unstable. That part is unambiguous. But even if all the lambda i's are less than 0, we are not sure whether the flow is the system is really stable or not, for the following reason. There are two reasons actually. One is that we have assumed the perturbations to be infinitesimal. So you may argue that, well, we have analyzed the stability of the flow only to infinitesimal perturbations, so what will happen if the perturbations are finite? That's a valid question. So this is one of the shortcomings of the normal mode analysis, in the sense that we cannot predict for sure if the normal mode analysis predicts the flow to be stable, that in reality the flow is indeed stable, because there may be instabilities to finite amplitude disturbances. Second, we are neglecting or ignoring the possibility that there may be transient algebraic growth but eventually resulting in a decay. This is because in reality the initial, you have to do the superposition, right? You have to do the superposition like this. So even if all the lambda i's are negative, or the real parts of all the lambda i's are negative, the summation of these, if vi's are not orthogonal, can lead to a temporary growth. It's called transient growth, and or non-exponential algebraic growth or non-modal growth, because it is not the growth due to one single mode or one single eigenvector. It is due to a combination or superposition of eigenvectors. Okay. So these are the drawbacks of the normal mode analysis. Now going back to the fluid mechanical problem, here again what we will do is we will not use this expansion. We will simply say that any perturbation can be written as some f cap of z, which is the finite direction, e to the I k x x, e to the I k y y, e to the s t, for the problem that we just discussed. Okay, x and y are unbounded directions and z is the bounded direction. Therefore this is the eigen function in the z direction that must be calculated or solved for, and the eigenvalue is the growth rate. Okay, so no need to satisfy, no need to worry about initial condition. Okay, now to illustrate all this, let's consider a simple model problem which has no physical significance, but it will help you to understand the method of normal modes in the context of a simple partial differential equation. Consider that you have a partial differential equation which sort of is like a dummy version of the NavierStokes equation. let's call it 1 by r. R is like a parameter, like the Reynolds number. Okay, this is a partial differential equation, obviously, because you have f as a function of y, and time, and it's non-linear. Why? Because it has f squared. Now, what you'll do is that first find the, in order to solve this problem, and we have to specify boundary conditions. So let's assume that f of y equal to 0 is 0 and f of y equal to 1 is 0. That's the domain between 0 and 1. So here this is the control parameter. Okay, this is the problem. Okay, now first you solve for the base state, which is one of the simplest steady solutions of this equation. Okay, now you will note that the base state is obtained by simply f bar minus f bar squared plus 1 over r. Okay, let's consider the simplest case of a spatially uniform base state. What does it mean? It means that if something is spatially uniform, the derivatives are 0. That means you are left with f bar minus f bar squared is 0, f bar into 1 minus f bar is 0. So that means the two solutions are f bar is equal to 0, f bar is equal to 1. Okay, but f bar is equal to 1 will not satisfy this boundary condition, so you have to ignore this solution. Why? Because it does not satisfy the BC. Therefore, you will be interested in only this solution because it satisfies the BC also. Okay, so that's the base state we are interested in. Now, so the base state is f bar is 0. Okay, now let's look at introducing perturbations. You have f of yt is given by f bar plus f prime of yt. Okay, these are the perturbations. Now we're going to substitute this back in the differential equation. So you'll get the left side is equal to okay. So let's throw away terms that are irrelevant. df dt is 0, f bar is 0, f bar is 0. So what you are left with is equal to f prime minus f prime squared plus 1 over r partial squared f prime by partial y squared. Now this term must be neglected because it's non-linear. In a linear stability analysis, you're not allowed to have non-linear terms. That's the definition of a linear stability analysis. So we finally end up with this linear partial differential equation. Okay. Now right, so now the next step is you have to first let's use two approaches. I'm going to show you how to solve this using both the approaches. Okay, so let's first Okay, let me take a new page. So this is the equation we are interested in solving, subject to boundary conditions that f prime of 0 is 0, f prime of 1 is 0. So first I'm going to use the method of normal modes. Here there is only one direction, y, which is bounded or confined, right? So there is no need for Fourier transform. So the typical perturbation, which is a function of y and t, can be written as, right, some eigen function, which is a function of y alone, times exponential of st. This is the normal mode form of perturbations for this problem. Okay, now I substitute this back out here. Okay, now you will get partial by partial t of f of y e to the st is equal to f of y e to the st minus 1 over r. You'll have to take the derivative with respect to y, so e to the st will come out. Now because your the function f is only a function of y, the partials will become ordinary differentials. Okay. Now the left side, if you see what's going to happen to the left side, you will see that you will pull out a factor of, you take a time derivative. This anyway is independent of time, so you'll simply get f of y s e to the st. So if you see one common thing that is there, it is e to the st, that cancels out in all these terms, resulting in s f is f minus 1 by r. Okay, subject to boundary conditions that capital F of y equal to 0 and y equals 1 is 0, right? Now, so how are you going to solve this? Well,